Okay, so we'll start with the last lecture of today. So what we saw is we have to solve the standard problem C transpose X, Ax equal to B, X greater than equal. By the way, for Neminat's feedback, he didn't pick the call. He has to enable the feedback, then only you can give. So I don't know where he is. So you will give it in the lab or after the lab or on Monday whenever he remembers that he has to take feedback. And another thing is Surya Prakash has also not taken feedback for you. It's parallel, I think, right? So he is also requesting to take feedback. So they'll probably take for the two together, either after the lab or on Monday, just for you. So this is minimizing C transpose X. Ax would be, instead of solving this, we end up solving this problem, which is, we call it as the phase 1. C tilde X tilde, A tilde X tilde B, X tilde greater than 0, X tilde is XZ. Z is an augmented variable of R dimensions. E is a vector of all ones. Capital E is a diagonal matrix with plus ones and minus ones on the diagonal. This corresponding onto the sign of the right hand side B. So what we just did in the lecture before was that we proved that if you take all indices of the Z in the B set, then you have a basic feasible point to start the simplex on this. Now you will feed this guy to the simplex algorithm. This will take whatever steps it's required and find a solution. Is this LP feasible? Yes, because we were able to find a solution to this. This is anyways, if it's not feasible, you can't do much about it. But is this LP bounded? So if you look at the problem C tilde X tilde, it is actually minimized just E transpose Z, because X tilde is C tilde has one element is 0. So it's just E transpose Z. And we know that the Z value is greater than equal to 0, because that's the definition we have, and E is just plus ones, right? So what's the minimum value of this, which could happen, is just 0, right? It cannot go lesser than that. So the problem is bounded below. At least it will not go to minus infinity, which we saw in the earlier case, right? So the problem remains bounded, and if the problem is degenerate, then you will use pivots and solve it. And this problem will be solved. It will give you a solution. Now we have to connect it to the original problem. To be able to connect it to the original problem, I have written a phase called a bridging phase, and I have written this theorem which we are going to prove. It's a very small proof, but it has to be done before we move to the next step. So the theorem says that the phase 1 problem has an optimal solution of 0 if and only if the only original problem is feasible. If and only if means it goes both direction, which means if your original problem LP is feasible, then definitely this guy will always converge to an optimal solution of 0. If we know this will so for example, we will not work with a infeasible or unfeasible problem, right? Which means that once we prove this, we will be guaranteeing that this guy will converge to 0. Then why do we have to apply simplex to this when we already know it will converge to 0? Assuming this theorem is true, which we will prove, the other direction says that the original problem is feasible, then it will definitely converge to a 0 optimal solution. Then why do we have to solve it when we know the solution? Correct, that's a phase 1 problem, and the goal for it is to get the indices which will end up in the B set, which will help us figure out which indices should go in the original problem's B set. That is why we'll solve it, not to find a solution. We know that the solution will come out to be 0. But our goal is to get which index are in the B set, which are in the N set upon convergence, which will help us figure out which indices to throw as the starting point of the original problem. Does it make sense? Okay? We'll tell you all of this today, and I will not leave it open. So let's first try to prove this. We'll prove it both directions. The proof is not too deep. So we'll do the first direction. The first direction says that the phase 1 problem has an optimal solution 0. So this would mean C tilde transpose X tilde is equal to 0. Correct? This is given and we want to prove this. Okay. C tilde x tilde transpose is 0. What is C tilde? 0 E transpose. What is x tilde? X and Z. This is equal to 0. This is implying that E transpose Z is equal to 0, which is obvious that the optimal solution of this problem is 0. What does this imply? Why? Because Z is greater than equal to 0 and E is just positive once. So the sum of all positive numbers is equal to 0 only if all of them are 0. Correct? So this would imply Z is equal to 0. Now check the feasibility. Now we go to feasibility. We know that the phase 1 problem has converged to the optimal solution 0, which means that the solution which you get is also the feasible solution, right? It is a feasible, that's why it's solution, which means that whatever solution you are getting, whatever x and this z is equal to 0, would satisfy a tilde x tilde equal to b. This is feasibility of phase 1. This we know, because the solution is called a solution because it is feasible. Yes or no? So let's split this guy again. So we know this. So we also know that AE, X and Z is equal to B. Correct? So we also know that AX plus EZ is equal to B. What do we know about Z? We know this guy is 0. So we know AX is equal to B. This is what we had to prove because this is the first condition of the original problem. Right? What we also know from the feasibility of the first phase 1 that x tilde is greater than equal to 0. Correct? What is x tilde? It is x and z is greater than 0. That's a different story. We already know this is 0. So this is we know. So this implies that x is greater than equal to no. So this implies that the original problem is feasible. Everybody okay with the one direction? Now we'll prove the other direction. It goes the same way. Huh? Alright, so we do the other direction. You help me with this now. Now you know one direction very easily. What is our starting point? That the problem which I just erased, the standard problem is feasible. Hai na? So the standard or the original problem is feasible, which implies we know AX is equal to B and we also know X is greater than equal to 0. These are the things which we know. Hai na? And what do we have to end up with? That the solution of the phase 1 problem is 0, the optimal, the objective function value. What should I do now? Think. You should be able to think these small proofs. Like I said, in the optimization course, I don't know what Nevinath taught in the necessary and sufficient condition, but those proofs are not too deep. I mean, they are not 5 pages involved. Hai na? It's just half a page, 1 page, you figure it out what's going on. How should we go? What should the next step I do? Sorry? Yeah, we have to somehow bring x tilde into play, right? Because the phase 1 problem has x tilde and a tilde rather than a. So what I'm going to do, we know this. So I'm going to try to write it in the form of the phase 1 feasibility conditions. So I can write this as AE x0 is equal to B. Can I write this? And I can also write this guy as x and 0 greater than equal to 0. It's the same thing because z has to come to 0, which you have seen from the first part of the proof. We are just reversing the construction of the proof. I'm just rewriting it. So what I'll do is I'll write this guy as a tilde x tilde is equal to b, and I would write x tilde to be greater than equal to 0, where you know that your x tilde is x comma 0. So which means that the original problem was feasible. If you augment the solution of that with 0, you get the phase 1 problem as feasible. This is one solution. We don't know whether that is the optimal solution or not. Correct? From the original problem solution, we were able to get one solution of the phase 1 problem, which we know is feasible, but we still don't know whether it's optimal or not. So now our steps will be to show that this is the optimal solution of the phase 1 problem. Okay. Okay. So now let's go back to our phase 1 optimization problem, which is minimize C tilde transpose X tilde. So this is the objective function of phase 1. So which is nothing but minimize 0 E transpose X Z, correct? Which is nothing but E transpose Z. Correct? Yes or no? Now if I substitute this one solution which I got here, I get that this is equal to 0. Correct? This is the objective function value of one solution which is coming out from the feasible solution of the original problem. Now the question remains to answer is this optimal or not? Is it optimal? Why? Because you cannot go lesser than this, no? Z is positive, E is all 1, so you cannot go lesser than this, so this is optimal. Same arguments which we used here, na? So it's the same argument, we're just going a reverse direction. The book writes the proofs in 3 lines, but I thought it's better to be more explicit because the 2 directions are slightly different to understand. Everybody okay? So what is the big outcome of this theorem, or the proof of this theorem? What do you observe? That upon convergence of, first everybody agrees with me that the phase 1 the original problem is difficult to find a BFP. We transformed it to an n plus r phase 1 problem, which we will feed to our simplex, and it will converge to an optimal solution of 0. Now the optimal solution of the 0 would also ensure that the z variables are 0. Look at the proof. Correct? So you are kind of done. Because z was the one which was bothering you. If you drop all the z variables, you go back to your original problem, don't you? Yes. But there is a catch in this. You don't know upon convergence which indices of x plus z or xz as a vector are in the B set and which are in the n set. If all elements of the z which you're going to drop because z is 0, end up being in the n set, then you're good. You can carry the b which is coming, and from the n which was now n plus r n elements, you will just end up with n minus r. You drop the z completely. I'll write all that down. But is that okay? The observation is phase original problem BFP difficult to find. We end up with the phase 1 problem BFP easy to find. Upon convergence, the phase 1 problem will give me 0 as the optimal solution. Also, it will give me z to be 0. That observation is clear with everyone. Now we'll go to phase 2, and I'll write it down what I just said in case it went too over your head. Is that okay? Look, the idea behind teaching all these algorithms is that these kind of concepts will come into play in your real life. Assuming that you don't do an MBA and become a manager in PwC, for example, in case you end up just doing engineering as your job, or you start doing masters, or you start doing PhD or anything. I mean, if you don't completely give up technology, then whatever problems, new problems will use, some of these ideas may be useful there. So that is what it is. The goal is not that you want to take Simplex and go to your company and plug it in and say it's working, because you will not even need that Simplex. And like I said in the lab, Simplex is a suite of all these linear solvers which you will just call at that point of time, which everybody does. All right, so we'll do the last part, which is the phase 2, or we solve the original problem. So I'll just take a minute to remind you certain things. There are two cases which we have to. Original problem is removed. So this is the original problem. Minimize C transpose X subject to Ax is equal to B and X greater than equal to 0. And this is your phase 1 problem which you have solved. This is minimize C tilde transpose X tilde with is 0 E transpose XZ subject to A tilde X tilde is equal to B, or AE XZ is equal to B, and you have X tilde greater than equal to 0 or XZ together greater than equal to 0. Okay, so this was the original, this was the phase 1. Now our goal is, the whole story in Simplex is the indices. So we'll go back to the indices. So if you write the B set and the N set for the two problems, we're going to look at it. What is the dimension of the B set here? Should be R, which you have not figured out yet, which is this. It should be R, and the N should be N minus R. In this problem, what should be the B set? Again R, because the constraints, the equality constraints have not changed, they have remained same. So they do remain R. That is why we had taken the initial Z in the B set, and the N constraints were N, because they were N plus R elements total minus R, which will be N. Correct? Okay. So far so good. So we first write, since original is feasible, phase 1 converges to optimal solution 0, or in a bigger way, Z is equal to 0 and some X. Everybody, this is what we wrote. Now we'll work on two cases. Case 1, at convergence of phase 1, B has R indices from X and none from Z. Okay. So now what we are saying is, look, ideally in this B and N of the phase 1 problem, if Z is becoming 0 and your problem is not degenerate, ideally the Z should all go in the N set, right? Because N contains active and B contains inactive. So this is the case which I have written, ideal case, that if you don't run into a problematic algorithm or problematic problem, that some elements of Z might go in the B set. So we're saying at convergence phase 1, B has R indices from the X and none from Z, which implies the N has all of Z indices and sum of X. Correct? Because we're saying all active are going in the N set. And N set contains how many? N elements. It contains N elements. So then you are done. Because what you would do, you will reduce the problem dimension from N plus R, drop those Z which have gone into the N set. The N was containing N small n elements, and now when you drop these R elements out of it, how many elements will you be left? N minus R, which was needed in the original problem. Correct? We can work it out. Hai na? So let's check whether it gives the feasibility of the original problem, although we had done it in the proof. So I'm going to just write it down. Same thing which I had written in the proof, I am writing it again so that it becomes more explicit to you. The original problem was feasible. This is the solution. So this would imply that Ax equal to B, the original problem is feasible. We knew that x comma 0 is greater than equal to 0, which implies x is greater than equal to 0. So you just drop the z completely. Yeah. Okay, let me just finish writing this, then I come back to this. Huh? It's good you're asking. Anybody else ask? Na? I'll repeat it. Let me write this because this will finish this section. Okay. Forget your name. Adish. Okay, I'll repeat this thing for Adish, then I'll come back to what parts I've written. So I'll start again from here. You were clear with the proof, the second which we were saying, no? Phase 1 has an optimal solution 0 if and if the original problem is feasible. Okay. So what I've done is I've written the two together for you on the board. This is the original problem. This is the phase 1 problem. Original problem is C transpose X, Ax equal to B, X greater than equal to 0. The phase 1 problem has an extra set of indices Z, and that's why it says an augmented space X tilde which has X and Z, and augmented A which has A and E. Correct? And small e is vector of all ones. Capital E is a diagonal matrix with +1 and -1 corresponding to the side of the right hand side. Okay. Now, how did we choose the B set? The B set was, when we say something is a basic feasible point, we used to say that it has contained R indices because R was coming from the number of equality constraints which you carry. So the number of equality constraints carried here are R, and the remainder are the elements. This is n dimensional, so n minus R is the number of in the complement of the B set. When you look at this problem, it is X tilde. Correct? How many equality constraints do we have? No, we just have R, because the number of equations are not changing. No, the number of columns are changing. It is AX plus EZ is equal to B. The number of rows are the same. The number of columns are augmented with the Z. Correct? So it's still R. What is the total dimension of X tilde? It is X plus R, X dimensions, and the Z dimension. This is N and this is R. So if the total is N plus R and you subtract the R from the B set, it will be N plus R minus R and N indices. Everybody with me? Okay. Now what I am saying is, this we already proved in the second part, the bridge. We know that the original problem is feasible, otherwise we will not work on it. And it converges to a solution 0, we just proved. When it converges to the solution 0, it definitely has Z is equal to 0. We have proven this fact. Now the goal is how to get back to the indices of the original problem. That is what we are trying to do. So we are going to work on two cases here. Case 1, I am saying, assume that at convergence, the phase 1 problem B has R indices from the X set. How many indices it has? From X and Z, N plus R. Out of which we have to pick R which will go in the B set. So any of the R could go. Some from X, some from Z, all from X, all from Z, anything could go. But I have created a case explicitly saying all the R indices in the B set are going from the X. And we'll work on the other cases also. That's why this is case 1. Assume that. And none from the Z. Okay, so which means that some of the elements from the X, which is N minus R, and the elements of Z, which are R, which is a total of N, will go in the N set, which matches this guy, which says it's N. Everybody with me? So now what we are saying is that since your B set already contains R indices and you wanted R indices in your original problem, but your N set had become inflated with N indices rather than N minus R, you just drop the Z. Because Z is not helping you anywhere. It is not affecting your B set. So the only thing I want to prove is that it does remain, the solution of the phase 1 problem does remain as the basic feasible point of the original problem after dropping Z. That is what I am showing now. Okay. So to do that, I have to prove the feasibility and the basic nature of the original problem. Everybody with me? So to look at the feasibility, we know that the phase 1 problem is feasible, which means AEX0 is equal to B. Correct? This is the solution which you are getting from solving the phase 1 problem. Now once you expand it, you get AX equal to B, which means that this is true for original problem. When you look at the solution X and 0, you know that this is greater than equal to 0 because it's feasible for the phase 1 problem upon convergence, which implies that X is greater than equal to 0, which means that this part is done. for the original problem. Now we have to prove the basic nature. To do the basic nature, we are saying, does B contains R indices? Because we wanted R. Yes, it contains. All are coming from the X. So they do contain R indices. Does the complement of B contains active constraints? So if you look at the complement of that, it will have some elements of X and some elements of Z. These will be the N minus R elements, and these will be the R elements, making the total to be N. So if I have to look at the basic nature of the original problem, I will say just ignore this. The complement of the B set contains active constraints. Yes or no? The last thing remains is the matrix. So the B matrix now is A with indices belonging to the B set. This is the A and E, the augmented, because this side is all phase 1. This side I am proving that it's giving you the basic feasible point of the original problem. Now take the indices of the B set and pick from this. Can it come from this? No, because B is already containing elements from X, which means it has to come from the A set. And whatever elements of the A will come, the dimension of A is R cross N. And you're picking R columns out of it. Out of the N columns, you're picking R columns. So those R columns I am referring to as A hat. Is that non-singular? Yes, because at convergence it is giving you a basic feasible point. So take this A hat to be your A hat for the original problem as well. So just dropping the Z completely, you're good. Does it make sense? Any other doubt? I can repeat it. So the idea is that if your problem is not a non-degenerate, the problem is non-degenerate, it's not a degenerate problem where the B set keeps carrying 0 indices, then you will be good, because the Z index by default, all of them will go in the N set, and you drop it out. Instead of N, you will end up with N minus R and you're good. Make sense? The trouble will happen when some indices of the Z end up, the sum indices of Z end up going inside the B set. Then what do? Because you can't completely get rid of Z. Because if you completely get rid of the Z, the B dimension will not be R indices, it will be lesser than R. And you had to start with that. Is that okay?
Last point where you said that all the indices that we are choosing A hat will come from A.
Sorry, louder.
All the A hat that we are choosing will come from A only, not the
It will not come from E. Because E is corresponding to the Z. Z is not there in the B set, na? Z is already in the N set. Because all indices, B only has X indices. We have already assumed this in this case. Anybody else has a doubt? No doubt? Should we move on to the case 2? Okay. So I'll erase the case 1 and write it here because I want to keep this on the board. कोई आ तो नहीं गया? There was a class booked at 3:30. Okay, fine. We'll finish soon, है ना? I'll not take too long. Oh yeah, because A hat was non-singular, because the A hat was coming from the solution of the phase 1 problem. The phase 1 problem had to be a basic feasible point, which means A hat had to be non-singular. Now we're using the same A hat as the starting of the original problem, because the Z is no longer playing a role. I think I'll probably, instead of doing case 2, last time I did an example on the case 1 itself, because I'm seeing somebody getting lost. So let me write this example, then I'll write case 2. Or it's better to write here. If it's not clear, let's look at an example. So this is original, which is minimize C1, C2, X1, X2, subject to X1 plus X2 is equal to 1, X1 and X2 greater than equal to 0. So we'll write the phase 1. So minimize 0, 1, X1, X2, Z, subject to X1 plus X2 plus Z is equal to 1, and X1, X2, Z greater than equal to 0. Okay, so now whatever I told in case 1, let's look at an example. Those who are getting a little doubt, this will clarify that. So I've written a two-dimensional problem, C1 and C2. Also you can put numbers, I've just read them to be C1 and C2. There is only one constraint. What is n here? What is r here? 1. Okay, good. What is n in this problem? Louder. 3, no? X1, X2 and Z. So there 3, you have augmented it because there was one variable. R remains when. This clears your doubt that the equation don't change, the columns change of the matrix. So this matrix is 1, 1, 1. So 1, 1 was already there and another E matrix became 1. Okay? It became 1 here because this was positive. Had this been minus, it would have been a minus Z. Clear, everybody, where this is coming from? Okay. Now what we say is, this converges, not this guy converges to Z is equal to 0 and some X. Correct? So what was the case 1 we had assumed? Case 1 we had assumed that all indices of sum from X okay. This is the case 1, that Z is going into the N set. What is the dimension of B here? B set has cardinality as 1 and the N set cardinality is 2. The total should add up, no? It's 3. Which means now we are saying that B has all indices come from the X set. So what are the indices in the X set? X1 and X2. So without loss of generality, I'll say, let's say it comes from X1. I can write X2 also. Which means that N set contains without loss of generality, it contains x2 index and the z index. Correct? Now we'll say that the solution of the problem of phase 1 problem which is converged, we're going to pick the indices and make it as a starting point of the phase 2 problem. So we'll start with feasibility of phase 1. So the feasibility of phase 1 is, help me write, what is the feasibility of phase 1? It is this equation. It is 1, 1, 1, x1, x2 and 0. That's important, no? That is why we did all the work in solving that problem. If we are not solving to z equal to 0, then there is no point. This is equal to 1. The b remains the same. It's a feasible. The solution of phase 1 is actually feasible for phase 1 as well. Correct? What do we get? x1 plus x2 is equal to, what does this mean? It's feasible for the original problem. What was the second thing? x1, x2 and z is 0, greater than equal to 0. The feasibility are giving two things to us. So this would imply that x1 and x2 are greater than equal to 0. So aren't we done with the feasibility? The solution of the phase 1 problem is giving us a feasible solution of the original problem, which we knew from the theorem. Now we are working with the indices as well. We know which indices are falling and which are thrown out. Now what we do is, solution of phase 1 is also the basic of phase 1, correct? That is why it is a solution. Otherwise it will not be, because it's a basic feasible point. What was the first thing to notice? B has one index, which is x1. Correct? This is what we assumed without loss of generality, which implies this is true for original, because the original problem also needed only one index. So we have that one index. Correct? What do we also know? Not change the notation, stick to what I am writing. So I does not belong to the B set. What do we know? We have got x2 and we have got z. Both of them would be what? Both of them will be 0. Why? Because it's a feasible basic point of the phase 1 problem, no? If x1 is belonging to the B set, x2 and z are belonging to the n set. And when they are belonging to the n set, they have to be 0. Correct? Now what will I do? I'll say ignore this guy and use this for the original problem. Because there is no z in the original problem, I will use this fact, so it's true for the original problem as well. Everybody with me? There's very little space, but I'll try to still write it down. The last point is, what is the last point? The A matrix, right? So the B matrix is, what is your A tilde? It's 1, 1, 1, correct? It's 1, 1, 1. And now the index has to belong to the B set. Which index is belonging to the B set? 1, x1, right? This is the first index. So take this. Is this non-singular in this problem? It is not even provable because it's scalar. If it was a two-dimensional matrix, then I could have proved. So you get 1. So use this true for original problem. Whatever matrix you will get here will be the same matrix true for the original problem because Z is not playing a role here. Is it now clearer? Everybody 100% clear what's going on here? Okay. Should we move on to case 2? I'll not bang your head on the case 2 because case 2 is more involved. Like I said, it will need to solve an LP with a double-sided bounds. But at least I'll write it down. Till this point it will be exam. You know, if I ask something, I'll not ask for the case 2. I'll ask for the nicer case. This is a non-degenerate case where all the zero elements are going in the n set of the Z. This we are sure, yeah.
Technically, in the case when there is no role of Z here.
Technically it's not, but if you had not added Z, you would have not been able to find the basic feasible point of the phase 1 problem. Remember how did we start? All the Z elements were in the B set. Correct? That is how we found the starting basic feasible point. And upon convergence, we are saying all B elements have moved to the N set. So you saw the transition. You started with B, your B set having all the indices of Z because you were easily able to find the, and upon convergence, all the Z indices moved into the N set because Z had to be 0. And then you drop it. And then you have your starting point of your original problem. Is that okay? Any other doubt?
So is there a correlation that if phase 1 problem is degenerate, then original problem might also be?
I have not read it, but we can search it. I'll let you know Monday. I'm not sure. The degeneracy part is actually not well studied, so I can't tell whether that's true or not. All right. So we'll now write the case 2. So at convergence, P has R indices from X and Z both. So sometimes I discuss this also and I end up showing an example also, but I think we have already done too much on this, so we'll stop here. This is the degenerate case. Like I have not told you how to degenerate. The spelling of degenerate is also wrong. So this is the degenerate case because I've not told you how to fix a degenerate problem. We'll skip this. But the only thing I wanted to highlight is that if indices in the B set are coming from X and Z, you can't drop Z. That is important. Because then your indices set will not be R, it will be lesser than R. And then you are stuck. So in that case, there will be some swapping happening and something which is uploaded on the drive. So I think this is enough simplex, because I want to cover duality and interior point 1 and then QP so that you comprehensively know optimization, not just depth of 1 or 2 algorithms. Is that okay? So what we'll do is go to the lab and you work on your project. If you have any doubts, some people had emailed me. So I'll come around and you ask me. The template for the reports are already there. What is your last day of exam?
28th.
Sorry?
28th.
Which day is it? Thursday? So I'll make your reports due Saturday. Will that be okay? We'll give you 2 more days. Or you want me make it due the next week? Next. I mean, if next, what is you finish it and then give your exam? I'm just giving flexibility. I don't know. I think the grades might be due Monday or Tuesday, so I would need to check all the reports. So I need some time. So that's why I'm making it to Saturday. So you'll have Friday and Saturday to prepare the report in case you don't do it before the exams. Is that okay? I'll send an email with a link like Google form to upload. है ना? One report PDF with the person. Last time I forgot to ask you to upload the corresponding research paper as well. है ना? So the research paper plus the report in a zip file with the name, whatever we'll tell, that you upload. Huh? So we'll meet in the lab. Huh? Okay, thank you. Stop.